donations by people joining and being a member of NJAA, and there's a donation box in the back. So if you would please consider giving us a donation to help support our mission, which is to educate the public about the science of astronomy. Time's up.
Okay.
Actually, you still got 20 seconds.
There you go. There's a scientist brewing.
Well, I think the 20 seconds is up, and welcome everyone. I'm going to introduce tonight's speaker. This evening's speaker is Dr. Edward Schwieterman, Assistant Professor of Astrobiology in the Department of Earth and Planetary Service Sciences at the University of California at Riverside. Our speaker uses our planet, Earth, as a model to characterize Earth-sized planets in the habitable zones of their host stars. And he also has a special interest in searching for biosignatures. Everyone, please welcome Dr. Schwieterman.
Yeah, thank you very much, John, for that wonderful introduction. Yes, I'm Eddie Schwieterman. I'm an assistant professor, astrobiology, UC Riverside. It is very hot here. It's 100 degrees. I was telling John when he invited me, I actually have a connection to New Jersey, which is that my family lived there until I was 10 years old. So I actually lived in Landing for 10 years and went to elementary school there in the Roxbury School District. So I thought that was kind of a cool connection. Today, I'm going to talk about exoplanets and the search for life in the universe. I think one of the big questions we all have when we think about astronomy in the universe, not the only question, but one of the big ones is, what is the prevalence of life in the universe? Astrobiology is the study of the origin, evolution, distribution, and future of life in the universe. And of course, most of the universe is outside of our solar system. So if we want to know about the prevalence of life in the universe, and if we assume that life is at least somewhat like the life on our planet, then we're going to have to look at exoplanets, planets orbiting other stars, to understand what the prevalence of life is. And I believe this is a civilizational goal. It's going to be very, very difficult. One of the reasons it's so difficult is the fact just that a planet like Earth is outshone by a star like the sun by a factor of 10 billion. So that's kind of trying to look for like a firefly flying by a spotlight from many miles away. It's very difficult, but worthwhile because the goal is maybe understanding whether we're alone or not in the universe. So my research specifically, as John mentioned, is using Earth as an analog potentially for other planets. Not that we expect other terrestrial, that is rocky exoplanets, to be exactly like our own, but if we're going to find life somewhere, probably there's a certain set of conditions that that planet has to host. And Earth, of course, is the only planet we know of so far to host life. Certainly, it's the only global biosphere in the solar system, even if we find extremophiles clinging to life in the subsurface of Mars or something, that would never be able to be detected remotely. And so we can use models of the Earth and tweak little things and understand what kinds of features, what kinds of gases, what kinds of surface features, whether it be oceans or continents, or maybe even things like vegetation on an exoplanet, what things can be detected to what kinds of tolerances. So in other words, how capable do our future observatories need to be to detect the evidence of habitability and life? There are differences, of course. If we just put the Earth around the other star, we end up changing many things about the chemistry of the atmosphere, because the chemistry of the atmosphere is in part driven by the spectrum, the UV spectrum of the star that it orbits. And so we can use some computational models to understand that. And of course, I'm thinking about, other things, long-term cycles on planets, geochemical cycles that might be different if, for example, a planet like the Earth received a lot less light from its star, and maybe therefore would have to have a lot more greenhouse gases in order to be habitable. And that has consequences not just for the temperature of the planet, but also chemically, and maybe the kinds of life we'd find on such a world. And so in this talk, what I really wanted to do is start from where we are now and draw a line from where we are now, highlight some really recent discoveries by the James Webb Space Telescope, which is giving our first really solid look into potentially terrestrial planets orbiting other stars, and then end with the promise of biosignatures, a little bit of a review, and then sort of the roadmap to finding them. So we're living in an age of discovery in terms of exoplanetary science. We have discovered over 5,000 planets so far, and that's the confirmed planets. You know, we have many thousands of more candidates as potential planets that may be there, but we have to get more information just to confirm their nature. And you can see here is a histogram plotting the number of detections of planets as a function of year. They're color coded with the type of observation that was made in order to discover the planet. The red is sort of this radial velocity method. I'll discuss this a little bit. It's basically the wobble, the Doppler wobble in the star due to the unseen influence of the planet. Transits, that's the largest number of planets discovered is through transits. That's the green. And this is like a miniature eclipse. What you can see from this histogram is that one, you know, the field of exoplanetary science is not very old. 1990s, you know, the first pulsar planets were found, and then, you know, the first planet, hot Jupiter around a sun-like star, 51 Peg, found in the mid 90s. And then as we get to the present, we have, you know, these thousands. You can see kind of a slope change after 2009. That's when the Kepler Space Telescope launched, which gave us thousands of planets. And then in 2018, the TESS Transiting Exoplanet Survey Telescope launched, and that also gave us many, many more planets. So here's just a quick summary of these techniques. The Kepler and TESS spacecraft, those are the bottom, the top and the middle telescopes on the right side there. Find planets by basically miniature eclipses as the planet passes in front of the star, as seen from our point of view on Earth. It causes the amount of light from that star to dim very, very faintly. And this is actually, you know, depending on the size of the planet, if it's a big Jupiter, it could be 1%. If it's an Earth-like planet, it's a 1 part in 10,000. Okay, so this is a very, can be a very small dip actually, but because we have space-based telescopes looking and very, very accurate photometric precision, we can actually measure those types of things and get to even planets that are sometimes even smaller than Earth and detect them. And then over here, that's the radial velocity method. This is basically the fact that, you know, the planet is orbiting the star, but the star is also orbiting the common center of mass of the planet and the star. For example, for, you know, the sun and Jupiter, the sun is actually orbiting a point that's, you know, close to the sun's surface, basically. And so when if you were just an observer looking at the sun, you would actually see it making a circle. And if you were lined up the right way, as the star is coming towards you, it would be just a teeny bit bluer. And as it's going away from you, it would be a teeny bit redder. That's a Doppler effect. There are a couple other ways that we can find planets. One of them is microlensing. And so this is the idea that Einstein, you know, promoted, that, you know, we all know is correct, which is that mass bends space-time. And through that bending, you can actually get a lensing effect. And so when a foreground object passes in front of a background object, you can get a very, very brief enhancement of the brightness of the background object. And based on the level, the timing, and the magnitude of that enhancement, you can understand properties of the planet. Now, you'll never probably see that planet again because these are very chance events. But what you can do with these microlensing events is build a statistical picture of how common planets are through microlensing surveys. And I won't talk about this much more, but what we've learned from these microlensing surveys is that actually there are an equal number of planets free floating outside the gravitational influence of a star as there are stars. That ejection of planets during planetary formation seems to be pretty common. So there are rogue planets. You may have heard that phrase before. And we know there are rogue planets, and we know their statistical, you know, distribution through these microlensing surveys. So that's why microlensing is important. And then, of course, there's the most intuitive way of finding a planet, and that's direct imaging. Right now, and that's taking a picture. So the challenge with taking a picture is that, one, the planet is faint intrinsically, and two, it is very hard to null out the light of the star, remove the contamination of the starlight to reveal that very faint signature of a planet. So right now we can find hot planets that are far away from their stars. So they're radiating at near infrared wavelengths because they're hot enough, they're young, giant, like Jupiter or bigger than Jupiter-sized planets, tens of AU away from their stars. And so that's the level at which things like Keck on Mauna Kea in Hawaii can detect. So we found several of these systems, really young, hot Jupiters orbiting at a distance of tens of AU from their stars. Why can't we do that for Earth yet? We can't do it for Earth yet because of the effect I mentioned. The fact is, Earth is 10 billion times fainter than the sun, and it's very hard to null out the light of the sun. Earth is actually much closer, 1 AU instead of 10 AU, and that compounds the technical problem. But we are developing the technologies in order to tackle that problem, which I'll get to at the end. And you may have heard of this thing called the Habitable Worlds Observatory. So I'll speak about that in just a second, or just a few minutes. But first, I want to talk about what planets are we finding now. This plot shows on the y-axis the masses of the planet in Jupiter masses, and the periods of the planets in days. And I've kind of marked helpfully where Earth is, and the type of method that's been used. And so what you can see here is the type of method is sensitive to different regions of this parameter space. So it's easier to find more massive planets with radial velocity, and they tend to orbit more farther away. It's easier to find larger close-in planets with transits. Okay, so that part is real. That part is real. We see some very massive planets close to their stars, but it turns out that you can't get too close. For most cases, Jupiters actually tend up being kind of rare. So there's only like a few % of them. That kind of statistics is real, but this observation that we don't actually have many true Earth analogs, that is, Earth orbiting sun-like stars at 1 year periods, that's a bias. That is because, one, we haven't been looking at long enough with sensitive enough technologies. And so we have a handful of these. We have found a lot of Earth-sized planets, but they are orbiting closer. That's okay, because some of them are orbiting these dimmer stars called M dwarfs, and so they're receiving roughly the same amount of light that we get from the sun. Anyway, so we know that there are an abundance of terrestrial Earth-sized planets. We know that there are many Neptune-sized planets. One of the really interesting observations that have been made statistically over the last several years in exoplanet science is actually the most common type of planet, statistically, intrinsically, is a planet that's intermediate in size between Earth and Neptune and Uranus in our solar system. We call it super Earths, or sometimes they're called mini Neptunes. And these worlds are the most common type in the universe, certainly of all the systems we've looked at, which is many, many, many thousands. And so we know that's probably real. And so the most common type of planet, we do not have an analog in our solar system. And this is one of the really exciting things with the James Webb Space Telescope, is that we will be able to probe the atmospheres of those most common type of planets and learn what they're made out of. So moving on here. So here's another way of describing these different types: terrestrial, Earth size, also Venus size. Important to know that just because something is the size of Earth doesn't mean that the prevailing conditions are the same as Earth. Venus, for example, it's hot enough to melt lead on the surface. It rains sulfuric acid. And so just being Earth size is enough to be habitable. It's really clear about that. So terrestrial means rocky. It means it's rocky. It probably has a volcanic outgas atmosphere, if it has an atmosphere. And then there's Neptune-like. Neptune-like means it has a hydrogen-helium atmosphere. And so they're called ice giants because they're mostly made of things like ammonia and water and methane, things that are found in the primitive ices in the outer solar system. But they have a big, massive envelope of hydrogen helium. They're gas giants that are primarily hydrogen helium. And then finally, there are these super Earths. And so super Earths could be large versions of terrestrial planets, maybe with some amount of hydrogen and helium they've glommed onto, potentially with conditions on the surface that are not too dissimilar from Earth, although they may be more like Neptunes, where they have enough hydrogen and helium where the surface isn't real surface. It's boiling hot because of all of the atmosphere. So again, we're going to learn a lot in the next several years about the nature of these super Earth type planets. One of the most, interesting types of planets, particularly for the public, is the terrestrial planets that lie at just the right distance where we could imagine there being liquid water on the surface. We have this conceptual tool called the habitable zone, also called the temperate zone or the Goldilocks zone. It's basically an idea that there's a range of distances where a planet with the right atmosphere, that's key, could have conditions that are suitable for liquid water on the surface. And we know that liquid water is a very key ingredient for life. And so we connect that directly to habitability. Now, what's important to know is, one, just being in the habitable zone does not necessarily make a planet habitable. The moon is in the habitable zone. It is clearly not habitable. It's too small to hold on to an atmosphere. That's one reason. Even if a planet were habitable, it's not necessarily habitable for you, right? A planet could be in the habitable zone. It could have a surface liquid water ocean and have no oxygen in the atmosphere. And so you wouldn't be able to breathe on such a planet. Or it could have toxic gases in its atmosphere and you wouldn't be able to survive. But microbes, simple life, may be just fine and they may produce abundant biosignatures. So it's important to know habitable zone doesn't necessarily mean habitable. Habitable doesn't necessarily mean there's life. And even if there's life, it doesn't necessarily mean that life can be life like us. There's a very interesting planetary system with several planets in the habitable zone called TRAPPIST-1. Something that's really important to know is that only a handful, basically, depending on how you count, 12% or so of stars are sun-like, but many more are smaller, redder, fainter, less massive, and longer lived. The most numerous type of star is actually called an M-dwarf star. Many of you know that, I'm sure. And as I showed in that diagram, where most of the planets we've discovered so far orbit more closely because they have transited more often, it's been easier to see them. The size of the planet compared to the size of the star is more favorable. Therefore, almost all of the planets we have discovered in the habitable zone actually orbit some of these type of stars, some of these less massive, redder, dimmer M-dwarf stars. TRAPPIST-1 is actually among the dimmest, faintest, and reddest of all the stars that can fuse hydrogen in its core. So it's an M8 star. Some of you know what that means, but it's basically just massive enough to burn hydrogen. Any smaller, and it might be a brown dwarf. What this diagram is showing is the scale of the TRAPPIST-1 planetary system compared to the scale of our solar system. Okay, so this whole TRAPPIST system fits well within the orbit of Mercury from the sun. But TRAPPIST-1, the star, is less than 1% the luminosity of the sun. And so to receive the same amount of radiation from the star, the planets can orbit much more closely. And so it turns out, depending on how you structure your habitable zone idea, and there are always ranges and uncertainties involved. And of course, remember, the planet has to have the right atmospheric composition to be habitable. Up to, a few of these planets, 4 maybe, could be habitable: D, E, F, and G. E, it turns out, is actually the one that is most Earth-like. This system, I will talk about a little bit more later, is really the most compelling near-term target to look for atmospheres on terrestrial Earth-sized planets. Caveat: if they have an atmosphere, we don't know that yet. That's something that we hope to learn with the James Webb Space Telescope. We know, or highly suspect, that the planet B, the closest one, does not have an atmosphere, that it's been stripped through stellar activity over geologic time. And of course, TRAPPIST-1 isn't the only system where we found planets that orbit at that right distance. And so here's a really helpful graphic from the Planetary Habitability Lab, Puerto Rico, that's showing many of the candidate habitable planets, right? So potentially habitable is really important to emphasize here. They orbit in the zone, doesn't necessarily mean they could host life or do. Really remarkably, the closest star to the sun, Proxima Centauri, hosts a roughly Earth-sized planet in the habitable zone of its star, Proxima Centauri B, that was discovered in 2016. Unfortunately, Proxima Centauri B does not transit its star, so it would be very challenging to characterize its atmosphere, something like the James Webb Space Telescope. But in the future, other space-based observatories may be able to probe its atmosphere. And then you can see here are TRAPPIST planets, and then there are many others. So challenging for atmospheric characterization is not all of these transit. And of the ones that do transit, they tend to be very far away. And indeed, they're too far away to get the right kind of signal to noise to probe their atmospheres and look for things like biosignatures. So that's why the TRAPPIST-1 system is really our best near-term bet for that kind of characterization. So far, the information we have about atmospheres has been limited to the Jovian type planets, made a little bit of the Neptune-sized planets. So these are our worlds where we have really, really nice information about their atmospheric composition. And again, they tend to be the gas giant planets, the gas giant atmospheres. They're puffy, they're large, they're big compared to their star. And that allows us to collect a lot of signal and get some exquisite information. The information that we had in the past was limited to things like Hubble and Spitzer Space Telescope. Now with the Christmas 2021 launch of James Webb, it's been operating now for some time. We've been able to get remarkable improvements in that data, and I'll show you exactly what I mean. So the James Webb Space Telescope is 6.5 meters in diameter. That's versus 2.4 meters for Hubble. Unlike Hubble, Hubble looks in the UV, optical, and a little bit into the near infrared. The James Webb Space Telescope looks primarily in the infrared. So just starting at the reddest wavelengths, about 600 nanometers, and then well into the infrared. In order to get the infrared wavelengths, it has to be actively cooled with cryogenic fluid on the spacecraft. That's one of the consumables that actually limits the lifetime of the mission, which we think was originally slated to be 5 years, and now we think we can get it to 10. It's stationed at the L2 Lagrange point, and it has many instruments that cover different wavelength ranges and are meant for different things. And can be used. Not all of these instruments are in all of their modes are used to characterize planets, because of course people are looking at James Webb, looking at early galaxy formation, looking at all kinds of things. And you can see in the news many of the discoveries that are being made outside of exoplanetary science with the Webb telescope. So when we're looking at a planet with spectroscopy that transits, what we're looking at is we're looking at the light that's filtering through the atmosphere as the planet crosses in front of the star. So I have a little video here. Hopefully it's running. So some of these wavelengths will be absorbed and some will be transmitted based on the opacities of the atmosphere that is controlled by the composition, the chemical composition of the atmosphere. So some molecules absorb selectively at given wavelengths, and based on the wavelengths that you receive and the wavelengths you don't receive, you can infer. And of course, we have libraries of what the spectra of all these molecules look like. You can infer the composition of a distant planet. And so that's just to say that, carbon dioxide and methane and ammonia and carbon monoxide and all of these things, and oxygen and ozone all have different levels of absorption. And they create their unique impacts. So here's another video that shows this. So you have light from the star. That's a continuous spectrum, if you remember that from school. Of course, there's a bit of absorption in the stellar atmosphere, a lot for M-Dors. That's actually hard. But when the light passes through the atmosphere of the planet and you subtract the light just from the star, you get the light from the planet. And you can look at this light from the planet only, and the selective decreases in intensity. Those are due to the molecular absorption features I mentioned, and infer the composition. So we see some bands from water, and we saw some from methane. And that's how we can understand how atmospheres were made out of. And so what I'm going to show you now is what Webb has done for exoplanet science. So you can see here, these are model spectra of different gas giant planets. So these are Jovian type planets. The dots are from Hubble in the optical. Okay. So we have many data points there. And then, but let's look in the infrared. Let's look in the infrared here. We actually have 2 data points. Those are from Spitzer warm Spitzer mission. Okay. And so all of this is just a model. So we're only getting constraints based on these 2 data points before James Webb. Now let me show you a spectrum of a planet that's only a 6.4 hour integration with the Webb telescope. And so this is a hot gas giant planet WASP 96b with just 6.4 hours of observation. We can see really strong water bands. Okay, so we can see the evidence of water, right? Important to know, we see water in gas giant atmospheres, doesn't mean they have oceans. Water is a very common molecule. It's one of the most common molecules in the universe, actually. And so this has nothing to do with habitability. It's just a very common molecule to find in any atmosphere, particularly those gas giants and hot gas giants. Moreover, we're seeing incredible things. So here's WASP 39b. This is the first detection ever of CO2 on an exoplanet. Okay, now when we go to terrestrial planets, we're going to look a lot for CO2. If you think about the planets in the solar system that have the terrestrial planets that have atmospheres, Venus, Earth, and Mars, we all have CO2 in the atmosphere, and that produces a strong signal at this 4.3 microns. This is exactly where we'll be looking for evidence of an atmosphere through transmission spectroscopy on TRAPPIST planets. So the fact that we can find it on a gas giant, it takes a lot less time, Webb time, to find this molecule on a gas giant, but the fact that we can find it and these data points are so good really gives us a lot of confidence that we can do the same thing with more observation time, more transits, a little bit more time with the terrestrials. And then another discovery that's been made with the Webb telescope is the first evidence of sulfur photochemistry. First evidence of photochemistry, that is the splitting apart of molecules by starlight, and then the combination into other molecules and constituents. And so sulfur dioxide was also found on WASP 39b. Actually, the first author of the paper reported in Nature is my postdoctoral scholar, Xiaomi Cai, who is at UC Riverside. And so this is an incredible discovery and just exquisite data. I mean, astronomers, if you could tell, forecast just how good this data is, they would be very pleasantly surprised. Okay, so we're getting really amazing data for the gas giant planets with Webb. Webb has been looking at some terrestrial planets. So here's an example. This is LHS 47b. This is a rocky terrestrial planet. It orbits far too close to its star to be habitable. It's got an equilibrium temperature of 586 Kelvin. That's compared to Earth's 288 Kelvin. What's remarkable is the fact that this planet is almost exactly Earth's radius, 99% Earth's radius. And that level of precision has been constrained by Webb in just a remarkable way. We have not seen evidence of an atmosphere, but with just one transit, we really wouldn't have expected that. And so this is just showing the difference between a CO2 dominated atmosphere, a methane dominated atmosphere, and a featureless model, either because there are high clouds or because there's no atmosphere at all. And you can see within the range of the data is not precise enough yet in order to discriminate between those models. What will have to happen is this planet would have to be observed several times in order to beat down that noise, in order to see if we can tease out evidence of an atmosphere. And of course, there are other targets to do that. So now that I've kind of told you what's going on now and kind of the remarkable things that are happening in exoplanet science, let's talk about what I came here to talk about, which is thinking about life on planets. How are we going to do that? And so I'm part of I'm an astrobiologist. I was trained as an astronomer. I have a PhD in astronomy and astrobiology from the University of Washington. What I love about astrobiology and exoplanet science, exoplanet biosignature science, is it's so interdisciplinary. That when we're thinking about how do we find life on a planet, how do we distinguish it between potential false positives, it's really a multidisciplinary endeavor. We need to understand, what life produces and in what quantities from biologists and earth scientists. We have to think about the geochemistry and the geology and the astrophysical factors that may impart what are called false positive biosignatures, or if you say oxygen is made by plants, and oxygen in our atmosphere is made primarily by life, bacteria, algae, and plants, but that's not necessarily the case for another planet, and so what processes could lead to abiotic oxygen on an exoplanet? How would we rule that out? Well, that's all really important. On Earth, of course, our atmosphere has been indelibly altered by life. This is a plot that's showing you the gases that are fluxed into the atmosphere, that are put into the atmosphere by life on on Earth today. That's the left, and on the right, it's showing a hypothetical Earth without life. And you can see that these bar graphs are very different. This is a log scale, okay, and so big difference here, in particularly in the oxygen, okay, and so the oxygen on Earth, primarily cyanobacteria, algae, plants. There's also a lot of methane. Those two made by methanogens. These are archaea, actually, mostly. And those two gases are in strong disequilibrium. So maybe we'd look for, the combination of those two things that at least indicates some very interesting chemistry. And so in order for us to have, a biosignature, we're not talking about things that are, very trace, that are not going to make an impact on a planetary spectrum that can be detected over interstellar distances. So when we're thinking about requirements for biosignatures, it needs to be produced by life, yes, but it also needs to produce observable features in the spectra that we can see remotely. It must be almost global in extent, because we're not going to get any spatial information from this planet. It's all going to be collapsed into either an annulus that we're integrating over for transmission spectra, or a spread of pixels that's really a point source that we're going to get direct imaging data from and put through a spectrometer. So it has to be global extent, has to build up to detectable amounts. And given context, it has to be separable from abiotic processes. So I have here, it's just an example: methane produced by life. Yes. Can you be measured from a distance by telescopic instrumentation? Yes. Have you ever been mistaken for a geological process? Yes. So that's bad. Methane alone isn't enough, right? Jupiter has methane, Saturn has methane, Uranus has methane, Neptune has methane, Titan has methane. None of those planets probably have life producing that methane. We know it's all from abiotic sources. So it's really the context that's important. That methane plus the oxygen on Earth, for example. And so the real question we're asking when we go back from the beginning is not what is the prevalence of life in the universe. Unfortunately, we can't answer that until we can send probes elsewhere over interstellar distances. But what we can answer is how common are planetary biospheres like Earth in the solar neighborhood, because that's something that we can actually answer through remote observation. So I spent a lot of time studying possible biosignatures. There are many different gases that are out there. It's not necessarily the case that the planet that we're looking at has to be exactly like Earth in every way, that it would have oxygen, or that it couldn't have higher abundances of other biogenic gases. Okay, so there are a lot of biogenic gases on Earth. Oxygen is important through photochemical processes that produces ozone that has signatures in different wavelength regions. That's really important. Nitrous oxide is laughing gas. That's actually one of the most abundant biosignatures in our atmosphere as a product of nitrogen metabolism. Almost basically all of it in our atmosphere is produced through life. That things like dimethyl sulfide, dimethyl selenide, methyl chloride, methyl bromide, methyl mercaptan. In some cases, maybe even things like phosphine or ammonia in the right context, just like methane, could be in combination with some other gas, could be considered life. There's things on the surface that we may look for. So there's something called the vegetation red edge. This is the contrast between absorption from chlorophyll and the intracellular scattering in the near infrared. So if your eyes were sensitive to wavelengths that were just a little bit longer than red wavelengths, you'd see plants as really bright, actually. And then temporal changes in those things, the changes in gases over a season or something, may also be potentially a biosignature. Importantly, all these things are context dependent, because we know that there are abiotic processes out there that can make some of these things. Okay, so here's an illustration of the red edge in the near infrared. So this is the part of the spectrum we can see. You can see there's a little bit of a bump in the green. That's why most plants are green. It's because they're just a little bit less good at absorbing green light than blue and red light. But then here, this is the red edge. If you look at this, it jumps up. The brightness of say a leaf will jump way up. And this factor is used in Earth mapping. So there's something called a normalized difference vegetation index, or NDVI, and it's used to map plant health on by Earth observing satellites, and really important for understanding changes in crops and forested areas, et cetera. And then on a global scale, if you integrate it over the entire Earth, because not an insignificant amount of the Earth, it has continents, and those continents have not an insignificant amount of vegetation, that this red edge is embedded in our spectrum. There are other kinds of pigments. Again, we could imagine a planet where some of these other things are more common. Things like bacterial chlorophylls that are from anoxygenic photosynthesizers. So I grew these in a lab in Scotland. And so these are actually, they're photosynthesizing, but they're not making oxygen. They're more primitive, maybe primitive types of life we would have found more easily earlier in Earth's history. There are also these archaea and algae in salt turn ponds that can turn bright pink and orange and all kinds of different colors. And so I actually consulted for National Geographic at one point, and we imagined what a planet would look like if it were covered in this haloarchaea that has the rhodopsin pigment, and it actually has a green edge rather than a red edge, and it appears bright pink or purple from space. So it's just something to think about in our sort of database of potential signatures. There's also the variation of both the surface signatures and the gases as a function of season. Now, this would be very hard to get, but it's worth thinking about. The carbon dioxide concentration, it's going up, of course, through our activities over, a secular way with time, but there's little oscillations embedded on that. And that's because, of the seasonal growth and decay of vegetation. And that changes the CO2 in the Northern Hemisphere by 1 or 2% over the course of a year, from fall to spring or winter to summer. And so that's something also that could potentially be looked for. And so the idea would be to look at a high fidelity spectrum of a terrestrial planet and get information that would tell us about the nature of its atmosphere, whether it has this edge effects from maybe vegetation, whether it has water, that's habitability, carbon dioxide, volcanic activity, and the combination of things that may suggest a global biosphere like Earth's, oxygen and ozone, produced directly or indirectly from living organisms, and methane in combination. And this is a real spectrum of Earth that was collected from actually Earthshine. So you're probably all familiar with Earthshine. You can see, the moon. I'm sure the effect the old moon and new moon's arms, where you can actually see the dark side of the moon because of the reflected Earthshine. Well, astronomers have taken that Earthshine and run it through a spectrograph, and that's what you're seeing here in these blue squiggles. That's the Earth's actual spectrum with some lunar stuff removed. So here's another view. This is a model of the Earth, but it's been validated, showing you some major features: ozone, oxygen. This is the oxygen A band. It's a very important target for looking for biosignatures. This is the ozone Hartley band. This is why this is the effect of the ozone layer. Okay, so this is why the very harmful UVC doesn't make it to the surface. But thinking about it, if it's blocked by the upper atmosphere and can't get to the surface, then it's really makes it those wavelengths very dark if you're a remote observer, and that would tell us that there's ozone potentially on that planet. Features from water, oxygen, CO2, a little bit of methane. Hard to find methane on modern Earth at these wavelengths. And so looking at this would be great. This is the kind of thing that we're looking for. I'll show you in a second what the signature will actually look like in reflected light. And of course, there's the false positive problem. I could give an entire talk on all the ways that people have figured out how to put oxygen in habitable planet atmosphere. It used to be thought, when we were thinking way back in the late 90s, early 2000s, about putting something called the TPF, or Terrestrial Planet Finder mission up there, that hey, as long as we're in the habitable zone and we've got abundant water, we're good. Probably, geologically speaking, no oxygen is going to survive. Our view of that is a bit more subtle now. We think that through a combination of orbiting stars with more far UV activity that can photolyze CO2, make CO plus oxygen, some of that oxygen atoms recombine to form O2 molecules or ozone. To varying degrees, varying predictions of that. That's over here. We think that, if you started with a lot of water, lost that water through hydrogen escape, which was, we think, what desiccated Venus. And if you started with enough water, you would lose enough hydrogen to leave behind enough oxygen to oxidize all of your surface sinks and maybe produce a massive atmosphere of abiotic oxygen. We don't know how common that is yet. This is one of the things we're trying to learn with James Webb Space Telescope. But if it is common, then it makes, it's kind of distinguishing the living planets from the dead ones maybe a little bit harder. And it really makes getting the two different gases and two different oxidation states very easy, or very, very important. But all of these abiotic ways of making, say, oxygen, leave behind telltale hints. So if you lose a lot of hydrogen and build up this huge atmosphere of oxygen abiotically, you probably have way too much oxygen to be biological produced. There's no way that you're going to end up with 0.2 bars of oxygen. So you might look for the signatures that indicate that there's a lot of oxygen in the atmosphere. There are these things called collision-induced absorption, and it goes up when you have a lot of a gas. And so, and it's proportional to the density squared rather than the density. It's technical, but there are certain signatures we could look for. We don't find them. It rules out that possibility. And then, of course, there are things that would rule us in. If you had oxygen produced, abiotically, and it was there for billions of years, then that's not really compatible with robust outgassing of reducing volcanic gases. And so if you find the reducing gases and the oxidized gases, that suggests that there's some continual replenishment mechanism for both of those things. And that best way to get that is life. And so people have done this analysis for oxygen and for methane. What contexts are these things biosignatures, and what contexts are they not? Methane in our atmosphere is very short-lived. It's got a lifetime of about 10 years. And so in order to have any impact on our spectrum at all, you need to make a whole lot of it. Way too much, thousands of times more than you can get from volcanoes, and maybe 10 times more or 100 times more than you can get from other types of abiotic sources. And so this is a really great thing. And you might say, oh, I'm so worried about these false positives. Well, we're thinking about them. So, it's much better for us to know about them now than having spent $10 billion on a telescope and it can't do this, disambiguation about looking for those other signatures that could give us clues about the provenance of those gases. Okay, so big question. When are we going to find biosignatures? Okay, well, we're probably not going to look at the reflected light spectrum of an Earth soon, maybe in 20 years. In the meantime, we can use Webb to look at a handful of transmission spectra of terrestrial planets. We'd look for something like the transmission spectrum. This is a transmission spectrum of Earth. You can see signatures of ozone. There's a little bit of oxygen in there, carbon dioxide, water. Not all of these things would be, necessarily detectable by Webb. I'll show you a little bit about what we think we can find. We think we can find methane, actually, methane and water and carbon dioxide together on an exoplanet, which may be a biosignature. So the TRAPPIST system, because of its close distance and because of the fact that we have multiple planets, is really the best planetary system to search for biosignatures in the very near term. There are some caveats here. One is we don't know whether they have atmospheres yet. We know that the B planet doesn't. There's some reason to believe now that the C planet doesn't. It turns out, however, that if you do the geological modeling, the fact that the B and C planets don't have atmospheres would in no way really constrain the chances of E, F, or G having an atmosphere. So E, F, and G could have atmospheres while B and C don't. If you think about the solar system, Mercury doesn't have an atmosphere, but that doesn't say anything about Venus or Earth. And those are, in relative terms, the kinds of differences in insulation that we're talking about. So it's not bad yet, but still, we're counting on those planets having atmospheres. If they don't, that's okay. Science goes on. We want to know the truth, whatever it is. But let's say it does. Let's say those planets have atmospheres, and let's say we characterize them. What could we find? So this is kind of a technical plot, but it's showing the actual spectrum of an Earth-like planet, assuming it's exactly the same as Earth. No differences. These features here, those are specific molecules. So I can tell you this one right here is the 4.3 micron CO2 band. And then this envelope in light blue is showing what the near spec instrument on JWST could get us. And what it's showing is that we could get CO2 pretty easily. But what it's also showing is that oxygen is basically impossible to find on Earth at Earth-like abundances. And we're not going to find an Earth-like amount of oxygen on TRAPPIST-1e. In fact, if we found oxygen, it would mean that there was a ton of oxygen, probably would be very bad. But what we could find is methane and carbon dioxide together. The plot I'm showing you here doesn't show any significant methane. But there's one thing that I didn't mention, which is the fact, I did mention it earlier, that the spectrum of the star really controls the lifetime of the gases in the atmosphere. And so if we're orbiting an M-dwarf star, you actually boost up the lifetime of the methane molecule, and you would actually anticipate for the same amount of methane that's made on Earth, 1,000 times the amount of methane that Earth has in its atmosphere on a planet like TRAPPIST-1e. In that case, you'd definitely be able to find the methane. And the methane plus the CO2 in combination may be a compelling biosignature. I've also done some studies myself thinking about this nitrous oxide. Could you have enough nitrous oxide on TRAPPIST-1e to produce a biosignature? And the answer is maybe. So if you had just, Earth-like amounts of nitrous oxide, probably not. But if you produced more, which we think was possible or really did happen earlier in Earth history, then you could have potentially enough in order to be detectable. And so that's one of the things that, we've said is like, don't give up on these gases. It's not necessarily the case that the planet's going to be exactly like Earth. We could get a little bit luckier. So that's, the near term. What about the longer term? So search for biosignatures in the 2030s and beyond. So you may have heard the news that NASA has recommended the Habitable Worlds Observatory telescope that would locate and characterize 25 temperate, that's habitable zone, terrestrial planets around nearby stars and search for evidence of life and habitability. It would look at this type of spectrum that I showed earlier, the reflected light spectrum of the planet, and it'd be able to find oxygen. Oxygen would be one of the things that we would go for. Oxygen plus water, plus maybe the vegetation red edge, if we're lucky, things like methane also. So this is what the ideal spectrum looks like. And when you have to go through all of the signal to noise and everything, when you understand the actual instrument that will be in space, you'll actually get something like on the right plot, where you have noise, like we do for real observations. But despite this noise, we would be able to find water, oxygen, ozone in an Earth-like spectrum. This is assuming a planet that's orbiting about 30 light years away. We're characterizing it with an HWO-like telescope. We can get those gases. We can understand and find an Earth twin and get those three gases and quantify them in an atmosphere. And so that would be huge. I'd mentioned that the planets are not necessarily Earth-like. One of the other things that I'm involved in with many collaborators is thinking about what would the signature of Earth be like over time? If you go back 3 billion years on the Archean Earth, there was no oxygen in the atmosphere. There might have been a lot of methane. Intermittently, there might have been organic haze. It might have looked a lot more like Titan than it did Earth. And in that case, we'd again be looking for things like the methane and CO2 signature. And so this is in a report that we have, a report that was issued for the LUVAR telescope, which is kind of the precursor, along with HABEX, the precursor kind of concepts for what the habitable worlds will be. I anticipate the name will change, at some point too. But the point is, there are many different possibilities for what these planets may look like. They don't have to look exactly like Earth for us to find compelling indications of life. And the last thing I'll say is that we haven't forgotten about intelligent aliens. I think it's maybe less likely that we'd find them on these planets that we're looking at. I think, things like radio SETI or laser SETI have a lot more chance of success. But conceivably, you could also look through in the atmospheres of these planets for things like artificial molecules, things like sulfur hexafluoride or CFCs or something like that, that would impart very weird signatures in the spectra. You could also use these telescopes to search for lasers at a given wavelength. Like a green laser only needs like really low wattage, tens of watts, something like that, to outshine a star at a very specific wavelength. And with a space-based telescope with a coronagraph, you could actually see that much more easily than you could from the ground. People have done these calculations. That's an exciting thing. I don't have a lot of time to talk about that, but I just wanted, because I'm out of time, end with this summary. Remote biosignatures are a thing that we can possibly do in our lifetime. They're not going to be just single things. Let's find oxygen. We have to consider the context. And we're probably going to get hints of life before we're confirmed life. So we'll say there's oxygen on this exoplanet. It's really exciting. There are different explanations. One of the explanations is life. We have to, look for a longer period of time. There's just going to be a little bit of uncertainty as we get more information. But guess what? We're never going to forget about that planet. We're going to be characterizing it forever. JWST is going to provide the first look at these terrestrial planets in the search for biosignatures, but it's really things like the Habitable Worlds Observatory that are going to give us a robust statistical sample of the nearby solar neighborhood in search for planetary biospheres like ours. I think the fact that this could even be possible in the next few decades, even if it's a couple decades away, is incredible. We live in a wonderful, wonderful time. And so that's all I have for today. And I'll be happy to answer any questions.
Thank you very much.
Thank you.
A round of applause for the speaker. Thank you. Are there any questions here? It's got to be some questions. Young scientists are here, I know. You baffled everybody. Yes, please.
Yeah. So if you go back, I think it was like one of your first slides, I think slide 6 or so. Where you show the distribution of planets that have been found. Yeah. So I wonder if the uneven distribution there, do you think that's more physical in terms of what types of planets can actually form, or a limitation on our techniques of detecting them? I mean, for instance, would we find low mass, long period stuff if we used a different technique, or do those planets just not exist?
Yeah, that's a really good question. So there are some parts of the diagram that's real. So like this part, this kind of desert of planets, really tiny, like screamingly close to the star, that's real. And then this frontier up here, that's real too. I mean, this is partly the definition of a planet getting bigger. And then, as we get this valley here, that's also real.
Okay.
It's called the Radius Valley. This frontier that you're mentioning here, that is a bias. We should expect a lot of planets here. In fact, there should be a huge number of planets there, but it's really the fact that it's harder to find the less massive planets. The radius is related to mass. So, the smaller the mass, the smaller the radius. It depends on composition too. But we wouldn't, it's harder to find those through both RVs and transits. And then the longer the period, the more transit, the longer you'd have to be looking at the system. So, if you want to find something like a Jupiter, right, that's 12-year orbit, right? And you probably want to have multiple orbits to confirm the planet. So that's 25 years. That's about the age of the exoplanetary field.
Okay. That makes sense. Yeah. Thank you.
I have a question. You explained very nicely in transiting systems that at the bottom of the periodic light curve, you would take its spectrum. And
Yeah.
what that would mean is, of course, the planet or planets are right in the center, about the center of the star. Then you would wait, and when it levels out, when it peaks, then you take another spectrum, and then you massage it, you subtract. Okay, so how about a system like the TRAPPIST system, where it's a small system and you have multiple planets? I mean, I would imagine you get moments where 2 or 3 of them are in line. How is that done?
Yeah, that's very great question. So yeah, you cannot exaggerate how close these are together. In fact, if you were on one of the TRAPPIST planets, you could see another planet right, from the surface. It wouldn't just be a point of light. It would have spatial resolution. The astronomers, if they exist on such worlds, are having, really good planetary nights. But I guess their skies are really bright. So the deep sky people would be mad. But the fact is that you have to have very, very accurate ephemerides in order to understand when a single planet is going to be transiting. And that's just one of the many complications in observing this system. The other complication is the fact that these stars are very active. So, and it has star spots. And so are you looking at the signature of a star spot and confusing it for a signature from the atmosphere? And so stellar characterization is really, really key. Understanding the orbits of the planets and their timing is also very key. There's a lot of planning that goes into those observations.
Okay. Good point.
Are there any
I have
questions?
another question. Mike.
Hold on, John.
Oh, I'm sorry.
You mentioned that James Webb is located at L2. What's L2 and why it's located at L2?
Yeah, so there are these points of gravitational equilibrium that exist that we put things. So if you imagine that there's a point between the Earth and the Sun where you feel an equal amount of gravity from the Earth and the Sun. If you just draw a line between the Earth and the Sun, that's L. It's closer to the Earth, of course, because the Earth is less massive, and so you can be you have to be much closer to feel the same gravity. That's called L1. On the other side of Earth, there's this equivalent point that's called L2. And the reason why you'd put something out there is because you would want to one, reduce the amount of interference. So if you're in lower orbit, you have a lot of interference. Sometimes you're pointing at the Earth. You're getting radiation from the Earth, which is bad, particularly because you want to be super cooled. And so L2 allows you to station keep with Earth while being far away from Earth. And that combination of things it makes it a very attractive place to put a cooled infrared flagship observatory.
Thank you.
Thank you. Other questions here? Go ahead, John.
Okay. Back in our home solar system, there are two things. One is we look for sites in our solar system where life might be possible, and like Enceladus. We also include Titan, and Titan is pretty much all ethane and methane. I don't even know why it's included in that. Is it realistic to look at Titan as a possibility? I saw one article where it talked about a strange life form that might live there. I mean, it's all speculation. Oh, and I'm going to add something to that. Back a few years ago, on Mars, they said they picked up traces of methane, and I think they since reconsidered. But is that realistic also?
Yeah, so I'll start with Titan, and I'll say I agree with you. Titan is not a great place. The surface of Titan is not a great place to find life. It's it's very, very, very cold. It's something like 80 Kelvin or something. It's not quite cold enough to freeze the nitrogen molecule, but it's actually getting close to that. And it has a nitrogen dominant atmosphere like us with a bit of methane, a few percent methane. And it's cold enough that methane actually has its own hydrological cycle. So it's so cold, water ice is a rock on the surface. Methane is at its triple point, meaning you can find it depending on circumstances in the solid, liquid, or gas phase, like water is on Earth. The kind of selling point for Titan, yeah, people kind of allude to the life thing. It's not really possible. People have come up with, maybe idea. As my opinion as an astrobiologist, it'd be very hard to have life. What people think, though, is that it could have interesting prebiotic chemistry. Like there could be very interesting complex organic molecules, as molecules made of carbon, that may give us some insight into the origin of life on Earth. But yeah, the temperatures are really, really restrictive for life. Also, the solubility, dissolving something into the ethane lakes would be very hard. It's it's a nonpolar molecule. It doesn't act like water, and so it's not really a great solvent. Titan does have a subsurface ocean, we think. The modeling is consistent with that. So deep under the ice layer, the water ice layer on Titan, may be a cool ammonia water mix ocean. And possibly there could be some interesting chemistry or life going on there. That's probably a more likely place to find life. And potentially there's a place on Titan where such things, material has gotten to the surface. I mean, that might be worth looking for. Your question about Mars. Yes, it is a huge debate about methane. And it's a very complex kind of story. If you look, there have been kind of a couple decades of tentative methane detections from spacecraft or from ground-based observatories, and then when they go back, there's no evidence of that methane.
Yeah.
And then the Curiosity has found some in its instrument. Of course, it brought some with it in the instrument too. And then there's this the Mars Trace Gas Orbiter is looking at the same places where Curiosity is measuring methane, and it's not finding it. And so there are these ideas for how that could be true. Like there's a very small amount of seepage from the surface. It could be abiotic or it could be biotic, who knows, that gets stuck in a boundary layer. So Curiosity can measure it, but it doesn't get high enough until that boundary layer disperses. And that it's a very small amount of methane. And so once it disperses, it dilutes. And that's why the Trace Gas Orbiter can't find it. That's the going explanation right now.
Thank you.
Doctor, one question on almost your last slide, you were showing, you had mentioned that a green laser with just a few tens of watts would be seen better than the star. Is that because it's coherent light? And
yeah, it's if you go to just a very specific wavelength, so of course it depends on the size of your, delta lambda, right? So yeah, if you cut a wavelength, yeah, and then you'd see an emission line effectively from the system, a coherent emission line, which you could also look at the polarization of that maybe. And so, yeah, there's some papers that have looked at, I mean, they're kind of, it's not something that I would say I would like put my bet on that we find it,
sure.
But it's free to look for.
Yeah, I know that SETI has been RF based for many years, and now there's a push for optical SETI for looking, and I'm assuming they're going to be looking for exactly these types of signatures that you're talking about here.
Exactly. And it's worth looking.
Okay. So should we on Earth, everybody has green laser pointers, should we all one day get out around the world and point at one spot in the sky and see if somebody shows up?
Yeah, well, legally they should be less than 5 milliwatts, right? So yeah.
Sure.
Are there any other questions here?
Were you suggesting at the end of your talk that within the next 20 or 30 years, there might actually be life discovered in some place and not just building blocks for life?
Yeah. So, I mean, the question that, so first of all, we may have more evidence from the solar system at that time. I kind of really wasn't talking mostly about that. That's a kind of a parallel track. I think it's very interesting. And we have, if we find life, I think anywhere in the solar system, it maximizes our chance of finding life elsewhere outside the solar system. But yes, so the question is, planetary biospheres, I think we'll understand whether they're common or rare in the solar neighborhood. So, we get this Habitable Worlds Observatory. Its launch date would be, realistically, probably somewhere in the 2040s. It sounds like it's far away, but if you think about the history of like gravitational waves or whatever, it took 50 years to detect them. That's kind of the scale that I think of for this. And yeah, if we get the Habitable Worlds Observatory, it'll be able to take these reflected light spectra of what we, of temperate zone exoplanets. If Earth-like planets are very uncommon. Yeah, it's possible we will not find them, and we'll know though that our Earth is kind of a very rare planet. I think that's useful to know. But if we do find something, I mean, it's very possible we, in that survey of 25 planets, that we do find something very compelling as a sign of life.
Yes.
Do you think we would ever find some kind of life that would have even near our own technological, even within several centuries of our own technological,
Yeah,
whatever, or
yeah, I understand what you're saying, because it's like the topic of all our science fiction. We'd love to find not just aliens, intelligent aliens, but aliens we could relate to. I happen to be of the opinion that it's probably really, really unlikely that we'd find a civilization that's really close to our level of technology, because if you just think about the cosmic calendar, if you collapse the whole age of the universe into a year, solar system doesn't even show up until September, life, in October, complex life in the middle of December. The dinosaurs died December 25th. Human lifetime is 0.2 seconds. In this scheme, it's very unlikely that somehow, in our universe of, in our galaxy of 400 billion stars, that we're going to be right close to someone who's right on the same track that we are. I think they're either going to be simple biospheres that we find, maybe there'll be complex life, maybe not, or they'll be very far in advance of us, unless there's something weird, and I keep an open mind.
well, so kind of what I understand you're trying to say is everything you're talking about is a much better way of looking for life out there, really, than, let's say, SETI, that's looking for signatures from a similar level of technology that we have.
I would say that they're complementary. I would say that they have their unique strengths. So SETI doesn't necessarily need to find something that's within a few centuries of us. I mean, they're looking for things like megastructures, which would be, millennia or even millions of years in advance of us, right? And they can look much further distances. So they could look for, way past the kind of few hundred light years that a space-based mission to look for simple biospheres could look. Okay, so I think it requires there to be those things out there, but we don't know until we look. I think it's a complementary way of looking for life. If there's advanced life out there, then it probably means simple life is common. If simple life is common, then there should be biospheres. And, if you're going to eventually evolve intelligent civilization, you need to have a planetary biosphere. It can't just be extremophiles clinging to life in the subsurface. They're not going to invent radio technology or space travel. So if we think that civilizations are common, biospheres have to be very common. So most of the history of the Earth did not have an intelligent civilization on it, but it did have microbes pumping gases into the atmosphere. So let's look for microbes pumping gases in the atmosphere about nearby planets, while we're also looking for those radio signals and laser pulses.
Right. Any other questions? All right. We very much appreciate, wonderful talk. Thank you very much. A wealth of information.
Thank you.
And we can't thank you enough for taking time and speaking with us this evening.
Thank you. It was very lovely to speak with you.
Thank you very
Good night.
much. Good night.
Good night, everybody. Before we all take off, does somebody drive a Mazda? A Mazda. Yes, you're blocking somebody, and if you would mind just moving your car for them so they can get out, that'd be great. QOs, who's our QOs this evening? Where are they? All right, so we have a 26-inch telescope upstairs, and we have Luna 2 out there. Could you just take a peek and see if they got Luna 2 open? And if you would go upstairs, go out this door up to the right, see the 26-inch telescope. Okay, and then when you come down, they have some other telescopes outside. Thank you very much for being here this evening. We appreciate it.
Sorry?
Excuse me, yeah. Lights on, fill everybody's eyes, and then vision. The door keep going up to the right.
Yeah, yeah. There's also one outside you can look at.
You're sending them out the back door.
I'll show you where it is.
I am. You are.
Thank you very much. I appreciate it.
There you go.
Hope I didn't put you out too much.
Not at all. Glad we found it.
It's right over there.
Yeah.
That's right. Oh, thank you
Yeah,
very
glad
much.
we found it. All right. What do you think, guys?
Very good.
Fine light.
It's out there. It's out there. Statistically, it's out. Yes. It's something I heard recently. I can't remember where I got it about. Was that we may be about 5 billion years too late. Because in setting stars. Like would have been favored in the last second.
You know, everything is moving. And around where it's backwards. At the end of it's some point in time, very dark.
Yeah.
Right.
Doug?
We didn't see them really that.
I'm going upstairs.
Yeah, the technology is getting better and better.
The technology.
You know, that's a big key also.
James Webb is a big.
Yeah. Until like here. You don't get to, yes.
My smiley son, that's okay.
Well, it's not okay, but we-
Oh, that's.
There you go.
We've not renewed our membership.
We do that all.